Good morning, teacher. My name is Tran Thi Phuong Anh. So today I want to present about my topic is one-step synthesis of rice husk chair iron oxide nanocomposites using ultrasonic-assisted co-precipitation method and its oriented application for removal of sulfamethoxazole in water. So today I have four parts for this presentation. The first is introduction, the second is experimental, research, result and discussion, and the last is conclusion. For the introduction, nowadays, water pollution by antibiotics is becoming a global concern due to increasing levels of antibiotic in water. Sulfamethoxazole is an antibiotic belonging to the sulfonamide group, widely used for treating infection in humans and animals. Additionally, it is used as a feed additive in livestock to promote the growth and weight gain of animals. Before the removal of sulfamethoxazole is an urgent requirement for environmental list because the presence of sulfamethoxazole residues in water can lead to antibiotic resistance, resulting in harmful superbugs for both humans and animals. Many techniques have been developed and used to eliminate antibiotics, such as biodegradation, photocatalysis, advanced oxidation, and adsorption. Among these, absorption using activated carbon or nanostructural metal oxide material for their combination like titanium oxide with carbon nanotubes. Titanium oxide or tungsten is frequently used to their high treatment efficiency, low cost, and environmental friendliness. However, the general efficiency of sulfamethoxazole treatment is still low. The material fabrication process involves multiple steps, making it time-consuming and costly, and it is challenging to recover the material after treatment. One of the approaches to overcome this limitation is to modify material with the ability to absorb magnetic nanoparticles to create material that can be both easily recovered and have large surface area. Therefore, research to fabrication of low-cost absorbent material for high efficiency and extensive reusability in sulfamethoxazole treatment is attracting the attention of many scientists. The use of ultrasonic waves to accelerate and short-term chemical reaction has opened up new prospects in material fabrication. When using ultrasonic wave, high saturation iron oxide nanoparticle can be produced at room temperature without the need of heat treatment. In this art, in this in this topic, in this research, I used the co-precipitation method with the support of ultrasounds to a composite nanostructural material of activated carbon iron oxide for the absorption treatment of the antibiotic sulfamethoxazole in water environment. Now we move to the section 2, is experimental. The first material, I used a rice husk collected from a rice milling plant in Thái Nguyên province in Vietnam. And the chemicals used is potassium phosphate monobasic, sulfamethoxazole, ferrous sulfate, heptahydrate, and ferric sulfate, potassium hydroxide, nitric acid, and these chemicals are highly purity and from the milk. And the water used in this experience is double distilled and deoxide water. The second is fabrication of absorbent material. Um, Rice husks are washed and cleaned, double-distilled water dried before being burned at a high temperature of 800 800 degrees Celsius for 5 minutes, rapidly poured into cold water before filtering, and dried at 80 degrees Celsius for 24 hours to obtain dry activated carbon. As you see in the picture A. To fabrication of absorbent material, are using activated carbon and iron oxide by the co-precipitation method from iron salt 2 and 3 solution. Weight 10 grams of activated carbon to 1000 milliliter glass beaker. Then add 300 milliliter of 0.5 m 0.5 m potassium hydroxide solution to the beaker. The mixture is placed in an ultrasonic bath for 30 minutes before slowly adding 350 milliliters of mixture of ferrous sulfate, beta-hydrate, and ferric sulfate solution in a ratio 3:1. The participant from reaction is filtered and washed several times with double-distilled water until the environment is neutral, and then dried at 80 degrees Celsius in vacuum for 3 hours to obtain the material denoted as RHF. The iron oxide material is fabricated in a similar process following the procedure above, but without activated carbon. The picture B is illustrate the manufacturing process. The methods for characterizing materials I use X-ray diffraction. Patterns of the samples were recorded on an X-ray diffractometer, and the morphological characteristics of the sample were investigated using scanning electron microscope and transmission electron microscopes, and the specific surface area of the sample was determined through nitrogen absorption isotherm at 77 K, and the saturation points were determined using a vibration sample nanometer. Material obtained under the different experimental conditions were tested for the ability to absorb sulfamethoxazole at room temperature and neutral pH conditions. Sulfamethoxazole solution was prepared at various concentrations, about 20 mg per liter, and 50 ml for each solution was added to each triangular flask containing 0.05 gram of the absorbent material. The mixture was stirred for 180 minutes. After absorption period, the sample was centrifuged at 6,500 rpm for 5 minutes, and the upper part of the solution was extracted for concentration determination using the high performance liquid chromatography UHPLC DP82998 from water. The solution will be analyzed was passed through a C18 column, with the mobile phase consists of solution of 0.1 mol of potassium phosphate monobasics per methanol, and at a flow rate of 0.9 ml per minute for 10 minutes at a column temperature of 30 degrees Celsius. The detection wavelength of the sulfamethoxazole peak was 210 nanometer, and the absorption efficiency was calculated by using this formula. While H is absorption efficiency, CO and CT are the initial concentration concentration at time t in the solution. And the next is results and discussion. From the SEM image, the small image as A in the left, it can be observed that the original rice husk consists of large sheets, while iron oxide is composed of nano-sized particles. After combining them, the rice husk sheets transform to a porous structure and interpress with nano-sized iron oxide particles. The X-ray diffraction shows the expression shows that characteristic peak of both iron oxide and rice husk are shown in the materials, but with a lower intensity. This may be due to the iron oxide particle being interpressed between or on the surface of the carbon sheet, as indicated in TEM results. And under the influence of ultrasounds and the Pietro experimental environment, the rice husk species are easily broken down into smaller species, and iron oxide form on the surface of this rice husk fragment, possibly through the formation of iron oxide and carbon bonds in the composite material, which will be further investigated through XPS and FTIR spectroscopy. The nitrogen absorption, desorption, isotherm, and the pulsar distribution of the material. The results indicate that nitrogen absorption occurs strongly from the beginning due to the presence of small pores in the material. According to IUPAC, the isotherm of rice husk of the material falls under type 4, characterized by the hysteresis loop of absorption. Calculated results show that specific surface area of materials is 89.41 meters square per gram, significantly lower than that of rice husk, and due to the presence of iron oxide nanoparticle that fills the voids in the rice husk. Observation in the small figure B, the figure B several that most of the material process have a diameter of lower than 20 nanometer, which opens up potential applications for various absorption process. And the picture A shows the hysteresis loop of and this picture shows the hysteresis loop and rice husk of iron oxide and these material samples. The results demonstrate that both samples nearly reach saturation in the saturated MS values at 300 being 55.07 respectively. The lower saturation monetization of the rice husk sample compared to iron oxide is attributed to the additional carbon component in the composites. With the saturation monetization values mentioned above, the materials are capable of efficient recovery. The ease of material recovery also helps prevent secondary contamination by the material itself. From this result, it can be inferred that the iron oxide molecule interact with the composites for the formation of the material composites with a high specific surface area, as well as the potential for efficient recovery and reuse after treatment due to an external magnetic field. Next is the evaluation of the absorption capacity of the materials. Research on the absorption and kinetic of sulfamethoxazole using different materials has been explored in numerous previous studies. To illustrate its practical application, the material was selected for testing sulfamethoxazole removal through static absorption, and the results are shown in the next picture. The results several that sulfamethoxazole absorption capacity of the material is significantly higher than that of rice husk and nano iron oxide. The material exhibits the highest absorption efficiency of 52.39%, which is 43% and 55% higher compared to the rice husk and nano iron oxide, respectively. It is noteworthy that even though material may not have significantly greater capacity than iron oxide, the main component of the material is rice husk with a relatively high saturation monetization, which make it favorable for recovery after the treatment process. Yeah, and for the calculation, the successful fabrication of composite material with nanostructure of activated carbon with iron oxide was achieved using the Co-precipitation method with ultrasonic-assisted. The rice husk and iron oxide materials has a specific surface area of 89.41 meter squared per gram and a saturation monetization and the capacity to effectively remove sulfamethoxazole achieving over 52% with an initial concentration of 20 milligram per liter. That's all about my presentation. Thank you for your attention. Wish you have a nice day. Thank you.